The Rock of Gibraltar. Standing at the entrance of the Mediterranean is a monolith of limestone. At 426 meters, it rises majestically over the straits. In the present day, Gibraltar is a flourishing modern city with a population of 30,000 coming and going, living their daily lives. Unbeknownst to many, a vast and complex group of caves crisscrosses the inside of the rock, formed over millennia by the elements that have battered the mighty stone. With 214 officially recorded sites, Gibraltar has one of the highest concentrations of caves in the world for its size. Full of intrigue, wonder, and natural beauty, these natural hollows offer an opening to another way of seeing the rock, an underground Gibraltar. Professor Clive Finlayson, director of the Gibraltar Museum, joins us one bright Mediterranean morning to tell us more about the forces that have come to shape the rock.
I think to understand the formation of Gibraltar, the rock, we've got to go back millions and millions of years. We've got to see it in different timescales, and then there are timescales of hundreds of thousands of years. But if we go back to the really deep time, then we've got to understand that we're standing and walking on basically an ancient seabed. Because limestone is formed by little tiny shells, calcium carbonate of little organisms, corals, that kind of thing, in shallow tropical waters, and where the light is sufficient for it to get to these things. And as these animals die and decay, they form this rock, this limestone. So wherever you walk on the rock, you're walking on an ancient seabed, which is quite a remarkable reading when you think about it. And we know from the type of rock that it is that it was formed in the Jurassic, which is maybe 200 million years ago. It's difficult to get our heads around these things, but that's probably when this rock was formed. But it wasn't up here, it was somewhere else. It's probably about 100 kilometers to the east of us, where we are today. It's a little microplate that people call the Alboran microplate. And what seems to have happened, because a lot of our geology and the shape of the rock, everything has to do with Africa. Africa's just there, and it's spent most of its life barging into Europe, pushing in. And something has to give. And in one of those moments, pushing in, push this microplate up this way and up. It obviously probably didn't happen in one go, gradual. And the microplate formed what we know as the Gibraltar Arc. So it's Gibraltar, Jebel Musa on the African side, North African side, and little other tiny remnants. That was the Gibraltar Arc. It's ironic, but if you go across the border into the hinterland of Spain, those are much younger rocks. The geologically there's more affinity with the rock with Jebel Musa on the other side than with the nearby hill. One of the things that happened when the plate pushed across is the arc closed the Mediterranean off. The Atlantic water that comes to the straits just closed up. And that went on for a long period, and what essentially happened was the Mediterranean dried up. It just almost became a series of shallow saline lakes. But then what happened was that gradually rivers started to erode onto the microplate, slowly, slowly, slowly. Eventually it opened up, the Atlantic started to flow in. Now people thought once upon a time that this took a long time, but the latest estimates published last year suggest that the Mediterranean filled in 2 years. 2 years. The waterfall here was 10 times deeper than the Niagara, but that was 5.3 million years ago. And that's the last time that Africa and Europe were connected here. There's always been a Strait of Gibraltar. So as you can see, the whole story of this limestone goes back a long, long time. But wherever you walk on the rock, we're up here, we see these cliffs. This is all evidence, and if you know where to look, you go with geologists, you can actually find specific evidence, which we'll see later on. Of this uplift, the rock is still going up. Africa's still pushing, and the rock is still being elevated, but of course at a very slow rate now compared to what it was before. What we've found is we've identified at least 5 units. We call them morphotectonic units, sounds good. But basically 5 blocks that have been pushed up at different points. So obviously the one at the top has been out longest. It was the first to be pushed up. And up there we may be talking of something that happened 5 to 10 million years ago. It's that old. Whereas the one at the base, where Gorens Cave, Vanguard Cave are, that is present day one, the one at sea level. So this is gradually getting pushed. And you see it, if you look at a profile of the rock from, say, near Europa Point looking up, you see cliff, slope, cliff, slope. Each one of those cliffs and slope was formed at sea level. The sea was lapping and eroding the cliff. All these cliffs were once down at sea level and were formed by wave action. And they've been pushed up. Once they're pushed up, then you have rockfalls and creating that slope above them. So whenever you see that sort of cliff slope, that's what you have. And that's the fantastic thing about the rock. It's one of the few places, I think, in the world where you can see it so clearly. Once it's explained to you like that, then you can say, wow, you know, this is really quite dramatic. The other thing that then happens superimposed on this at other timescales of maybe hundreds of thousands of years, and that you can see better further down, is sea level change. The sea level never came up this high. But we have variations in sea level. The sea level may have been as much as 5 to 8 meters higher than present day, and it went down by as much as 120 below. At that time, the beach would have been where those ships are out there. It's really quite remarkable. This all would have been land. So it's that interplay, if you like, between the rock being pushed up and the sea level going up and down that has created all this. The other thing, I mean, I always like to ask myself, why are things the way they are? I mean, I don't know if people ask themselves, why is the rock the shape it is today? It's conical and it's not symmetrical. It's sloping on one side and it's steep on the other side. Well, imagine it this way. As the rock's been pushed up, the bit at the top has been exposed to the elements for longer, so it's more eroded. So that's why there's less of it than below. And if you look out to sea, that way you've got 2,000 kilometers of sea. So the waves have a lot of fetch, a lot of energy. They have the potential to erode this side of the rock much more than the west side of the rock. So that's why initially the rock would have been like that, and it's been eroded much more on this side. So when we get rock falls in the winter and the rain, that's been happening for millions of years. It's part of that process. So that shape is not casual. It's to do with how much time the rock's been exposed and the angle of the erosion. The other thing, of course, is superimposed on this geological background is this amazing shape that the rock has. It sticks out, it has this very characteristic shape. And that has had importance to people for a long time. The Phoenicians were here maybe 2,500 years ago, and the whole idea of the columns, the pillars of Hercules, this one and the Jebel Musa, they didn't know it, but quite coincidentally the two pillars are of the same kind of limestone. They're quite unique, formed what was the marker, the end of the world for many people. So if you looked at the map of the world then maybe 2,500 years ago, or even a bit less than that, this was the marker, and this pillar was this signal to people. And the caves here were where they stopped and they made offerings, and it was one of the markers of the world. So we're quite high up the rock here. I mean, we're about 180 meters above present-day sea level. And when we look at a formation like this, you realize it's not your typical limestone. In fact, it's not limestone at all. In fact, when you actually hold it, you see it begins to crumble on you. It's sand, it's fossilized sand, what we call sandstone, essentially. So the question is, what's all this sand filling this cave, doing all the way up here, and how did it get here? Well, if we look at it in a bit more wider angle, what we see is that it's not horizontal. We can see the bedding lines, the slopes, as the sand had been sloping inwards towards the back of the cave. This is an old, ancient, very ancient sand dune. Now, for a dune to form, it needs to have sand coming in from the outside. Clearly, at the moment out here, we just have a cliff. So this was formed once upon a time, probably 2 or 3 million years ago, down at sea level, where Gorens Cave is today. You would have had a large sandy plain outside, and the dunes would have been moving, hitting the rock and piling up against the caves and then dipping inward towards the caves. At some point, all this was pushed up maybe not in one event, but probably in a series of events. And the moment that started, the dune died. There was no input into the dune from outside. And with the chemical action of rain coming into solution, carbonates forming, it hardened and hardened to become a dune. So it's not that the sea level was ever this high. Sea level would never have been up here. It's evidence that once upon a time, a couple of million years ago, this was 180 meters down. So it's, if you like, direct evidence of the kind of impact that Africa has been having on pushing and lifting the rock up. So we're here in one of the two Goat's Hair twin caves on the Mediterranean steppes, and it's a particularly good example of a marine cave. We're 220 meters up, we're more than halfway up the rock. So what is a marine cave? A cave formed by wave action doing up here. If we look around, there are no stalactites. This is nothing like St. Michael's Cave or a cave formed by solution. This was formed by waves coming into this cave and creating this very characteristic shape. On the left down there you can even see the marine notch, which you can see today in cliffs and caves at sea level. When the waves come in, they create this kind of shape, which we call a marine notch. If we were in Gorham's or Vanguard caves, this would be the back of the cave. It's got exactly the same shape. Gorham's cave at the back looks exactly like this. But of course Gorham's extends well out. We're here on the limit. What's been happening is basically that this cave and the other one, its sister cave, were formed at sea level by wave action millions of years ago, and they've been pushed up. Just like the dunes have been pushed up, everything's just been forced up. And then this continuous erosion from the east side, wearing away at the cliffs, the rockfalls, of which we still get rockfalls in Gibraltar now, have been eroding and eroding the cliff, and the cave has been collapsing. So what we have is the back end of what would have been once a huge cave formed by the sea and would have been at sea level. And I think it's just fantastic to find this kind of thing up here and show us the evidence that everything is all the time moving and changing, and the dynamics of it. I don't think there's a better place than Gibraltar to show you this kind of thing. I've been coming to these caves since I was a little boy. I love them. They're part of me, part of my personal heritage. I think they're wonderful things that we should be wanting to show to the people who come from outside, and we should all embrace them as a very important part of our heritage. We hope that they will become part of a recognized World Heritage Site. So it hurts me to see all this graffiti, people coming and splashing paint and putting their names on places like this. I mean, it's vandalism, it's wrong, it's illegal. But we should all care much more for our heritage than this. We're going to embark now on a project to actually clean all this, and I hope that all of us will see this as a very important part of our heritage as we walk past Mediterranean steps and come in here and treat it with the respect that it deserves.